remain unanswered. But for now, let me introduce our second invited speaker, Baron Peters.
All right, I hope that I have this working correctly.
This looks great.
All right, thank you so much for the confirmation. I have given these talks before and gone 2 minutes in and people say I can't see your slides. All right, so thank you. I'll be talking about a Diabat method for computing polymorph free energies. I want to start by thanking some of the many contributors to the work that I'll show. I will go through all of them at the end. I also want to thank Eli Lilly for funding the work. Along the way, I'm going to try to motivate some of the focus on thermodynamic properties here by talking about some of the things that I've looked at in the past. All right, so crystallization, of course, a tremendously complicated process, many different scales. You can think about the manufacturing chain, and I rarely do that. We begin to think about things when you start to look at the crystallizer scale and population balances, and the distribution of crystal habits and sizes that come out of the crystallizer, and also polymorphs. Those things are controlled by the nucleation and growth kinetics, and so we do a lot of work in those areas. And underneath all of it is the thermodynamic driving forces that really control everything. So this is a bit of an unusual focus for me. You've probably seen some of my talks in the past about rare events methods for studying nucleation. I want to key on one of these here. Up in the upper right, you see the seating method. Val's in the audience. She was on the original paper in 2012. That has come a long way. I think in the years since, we've learned how to set those simulations up so that we get reasonable agreement with experiments. So there was a methods advance there, but I think in some ways, one of the things that I like best about that work is the common sense advance of recognizing that if we want to get predictions that agree with the ones that agree with results from experiment, we cannot rely on comparisons of rates computed at an absolute solute concentration to rates measured at the same concentration. These will not ever agree because the force fields are not an accurate portrayal of the real properties of the system. And so when you set things up with a comparison at the same absolute concentrations, you're really working at very different driving forces for those processes. So, what you see down here on the bottom axis of a figure from one of those seating papers is that, we're achieving agreement in those cases where we do, not all of them. But when we do, it's because of the comparison at equal driving forces, equal supersaturation, basically. I want to show another example of that, and this is a calculation of spiral growth rates. We started with atomistic simulations, computed the elementary attachment rates, computed the Kink velocities and Kink nucleation rates, and incorporated all of these parts, starting with atomistic simulations and no adjustable parameters into the spiral growth theory. And what we get as an output is a growth rate that matches the ones seen in the experiments across a range of supersaturations. And we did that. They're all rate constants in the model, and so we only did one set of simulations. We didn't vary the concentration even. Once you compute a rate constant, it should be a constant if it's really doing the proper thing in the theory. So you see here that that's what's happening. You get a prediction of the growth rate, including all of these different processes along the way, and it actually matches the results from the experiments, which is something that I think is pretty exciting and definitely not been done before. I'll point out again that part of the recipe for getting these things to line up is not to compare at absolute solute concentrations, but rather to compare at the same values of the supersaturation. And I'll note here, this is sort of relevant to the talk that Jeremy just gave, is that we do have in this analysis an ion by ion growth mechanism, and it still looks like a quadratic dependence on supersaturation, and that has to do with that Kink attachment rate in combination with the Kink nucleation rate that sets the Kink density in the system. So, I don't know that that's a general conclusion, but you can get these curved relationships on supersaturation, superlinear relationships from a monomer by monomer attachment kind of process. But there, as I pointed out, there's a lot of different steps involved in those, and a lot of things to rule out. Would love to have an experimentalist like Jeremy has. Okay, so the point that I would make here at the end of this is that classical theories actually sometimes don't look so bad when you compare them to experiments at the same supersaturation, or more generally at the same thermodynamic driving force. And that in order to do that, though, we really have to be able to precisely pin down what the solubility is and chemical potentials of our solutes in solution in the solid forms in order to determine where we live on the supersaturation axis for a given simulation setup. So I want to really drive this point home with this little example. Okay, so rare events is something that I think about all the time, and rare events kind of come as really, really rare events, and also all the way down to medium rare events. So we have here on the upper left, we have a reaction. This is a potassium permanganate in solution with citric acid, an excess of citric acid. It's about 1 millimolar of permanganate in this case. And so you can think about the volume of the flask and the time, hundreds of seconds, that it takes for this solution to turn from pink back to the color of just the citric acid with all the reduced permanganate. And you can make a ballpark estimate of what was the rate of the reaction that was happening in there. Of course, it's changing over time, but the sort of characteristic estimate here would be about 10 to the 19 events per liter per second. And everybody agrees that reaction rates are examples of rare events, and yet that seems pretty fast. Now, in nucleation, we have something very different. You have here a levitated droplet. This is in a paper by Lee and coworkers in PNAS. And here the volume is much smaller. The time is longer, but not too much longer. Thousands of seconds, you watch the droplet and nothing happens, and then in a matter of 1 second, nucleation occurs and grows to completion. So in this case, you can make a ballpark estimate of what is the rate of that process, and it's only about 10 to the 3 events per liter per second. And I think that there's this 16 order of magnitude discrepancy between nucleation processes as rare events are extremely slow. They're like the rarest of the rare events in the context like this, versus reactions, which are rare events, but they're relatively fast. They're really on the order of a mole faster, and that's because you have something on the order of moles of millimoles, maybe of molecules over here, any one of which could become the core of the final nucleus, and you're waiting for the first one to do it, and then the whole process is over. On the left, all of the molecules have to go through this transformation for you to say that the process is over, and so this leads to very, very different kinds of rates. This has, of course, giant implications for the computational requirements that you need to do this by brute force. Things are already out of reach for the reaction case, the medium rare case over here, but they're astronomically out of reach for the rarest of rare case over here with nucleation. I think it also has implications for the conclusions that we draw about classical versus non-classical nucleation mechanisms. So there are lots of cases where we see images and instances of non-classical nucleation pathways, and I really appreciate, as in the talk that Peter gave this morning, he goes through and actually estimates the rates of those processes where he's seeing the non-classical nucleation pathways. And what you typically see is that they're over here in the medium rare case. The rates that he reports are closer to 10 to the 19 events per liter per second than they are to this extremely rare case. And I just say this to point out that that the classical theories were built and constructed with this situation in mind, that nuclei are extremely rare. They don't see anything around them except an expanse of open solution, as opposed to various things in the cryo-TEM environment and other solid interfaces, droplets around in the environment. So, even though the non-classical pathways are real, there are also real situations, I think, where the classical mechanisms might actually still be applicable and useful frameworks for thinking about things. Okay, so before we can do that, before we can make a connection between theory and simulation on any rigorous grounds, we again have to be able to specify the driving forces in our simulation. That's in terms of chemical potentials. We want to be able to compute those for any molecule in any solvent for any form, and that's sort of the goal that we've been chasing as part of this Eli Lilly project. There are several different parts of this challenge, right? So in order to do this, first of all, you have to be able to compute the chemical potential of the solute and the chemical potential of one solid. And then we'll deal with the problem next about going from one solid to another solid to another solid, okay? So there are a lot of strategies for doing this in the literature already. A few of them I think are a bit ill-advised. You know, the idea that you can go directly from the fluid to solid along a free energy transformation pathway is really fraught with problems. We have tried that ourselves and run into problems. We have picked up results from others and didn't know that they had problems that they didn't know about and built them into our own results and caused us problems down the line. The point is that you have various features on surfaces that lead to metastable features, and direct coexistence simulations can fail because of those, like kinks and pits. You have really terrible phase space overlap because the number of translational and rotational and vibrational degrees of freedom are different when you're in a solid versus when you're in the liquid. And so these routes tend to be very difficult. So I think the more reliable route is to start with two reference systems. And, you know, the familiar one to almost everybody in the call here is going to be to start with the Einstein crystal and transform that into a model of the real crystal with the interacting molecules and bonds and all of those things, okay? And you know, I will have more to say about these later. But, you know, what is almost so easy that we don't think about it is that we also use a reference system in the gas phase. We start with an ideal gas model. We include an internal partition function, usually using some harmonic approximation, and we get the free energy of the gas molecule, and then we do a solvation free energy calculation, and we compute the free energy in the solution phase. That approach works great as long as you're working with very small molecules, and in fact, that's what people have done, is confine themselves to doing these calculations for extremely small molecules. When, you know, we started this Lily project, we had obviously an impetus to do things that were a pharmaceutical level of complexity. And as soon as you get one or two of these rotamers and different degrees of freedom that are definitely not harmonic, you run into problems with this approach. So we developed this thing called a centroid. It's a bunch of atoms connected to their center of mass by springs. And the advantage of this is that we can immediately plug this kind of model into our thermodynamic integration machinery and get the free energy of the absolute chemical potential of our model, and then solvate it using standard methods. Why does it work? Why does it work well? Because it gives you, by construction, good phase space overlap. It has the same number of rotational, translational, and vibrational degrees of freedom as the final molecule, and that's what really helps the thermodynamic integration to be done so efficiently. Okay, so this is, the rest of this, what I'm not showing here, are the solvation part of this calculation. That's very well established machinery at this stage, and we're just using mostly off-the-shelf machinery from Mobley and others' shirts. And you can see that, we've got it working in lamps and Chromax and various platforms, and it gives us agreement in both cases. All right, so can we do this? Can we do this for multiple solids now? So in order to go from solution to solid to any solid, we have to also, in thermodynamics, it doesn't matter how we get from one place to another. So instead of going from solution to all solids, we can go from solution to one solid and then try to devise ways of going from each of the solids to every one of the other solids. So the usual way of thinking about doing this is to start with something, go back to the machinery of Frenkel-Ladd, for example. You have polymorph A, you can transform that to your Einstein crystal. You can go back from the Einstein crystal to new polymorph B, and then you subtract the two free energy differences that you computed here to get what's usually a very small free energy difference between polymorph A and polymorph B. Okay, so a lot of variations on this theme. These are reliable methods for the most part, and I think that we use a lot of them in order to check the things that I'm going to be showing you later. But while you're doing them, you can't help but wonder, why am I taking this long walk to the Einstein crystal and back every time? I should be able to exploit the fact that the interactions here are similar to the interactions here and have some direct pathway. Well, there was a beautiful paper that I read about 20 years too late. I wish I had discovered this a long time ago. This is this lattice switch Monte Carlo idea that gives you a direct path to go from A to B, a very general construct. And what's cool about this is not any particular advanced sampling methodology behind it, but the order parameter itself. I'm of the opinion that among this advanced sampling world, after 40 years of effort, umbrella sampling is still as good as all the competitors. And what really drives improvements is largely the order parameters that you use to sample along. So I think that this is an example of that they really just provided this very clever order parameter to use for your sampling. And it's kind of hard to imagine, but I think that you like it after you think about it for a while, at least I do. So if you imagine a simulation of polymorph A, the atoms are, in thermal motion, they're never sitting at their 0 Kelvin lattice positions. They're always displaced from those a little bit. And what Wilding and coworkers envision doing is taking the instantaneous displacements, let's call them U, and imposing them on the 0 Kelvin lattice of the other polymorph B. And when you do this, of course, polymorph A was relatively happy with those displacements because they're thermal equilibrium displacements. Polymorph B really doesn't like them, right? And you can imagine doing this process in reverse as well. What they did was they said, well, let's compute the energy in polymorph A with these displacements, compute the energy in polymorph B with the exact same set of displacements, and subtract the two. And you get this delta E order parameter. They used this as an order parameter, and they showed that you could drive the system from polymorph A gradually towards polymorph E by sampling through any method that you choose along this delta E axis. And they talked in their paper about the importance of these gateway states. So the typical displacements are very A-like when you're over here in basin A, and they're very B-like when you're over here in basin B. But at the top of the barrier here, and this barrier has no kinetic relevance whatsoever, but at the top of the barrier, you have these displacements that are equally likely to be seen in either of the two polymorphs, and they called these gateway states. Now, when I read this paper, I got really excited about this because I recognized that this delta E is a vertical energy gap, the same object that has led to so many advances in the theory of electron transfer. So if we just take a little sojourn here to the theory of electron transfer, I will make this brief. But you see always these two parabolas representing the free energy in the reactant state when you have a donor and an acceptor with the donor holding the electron. And then you have another parabola for the product state when you have the donor and the acceptor with the acceptor already having received the electron. So the Hamiltonian in these two cases has changed because it has different electronic parts, basically. So, this bottom axis here is a vertical energy gap, and it gives rise to two different free energy curves, depending on which state the system is in. And that vertical energy gap is exactly the delta E that you see in the lattice switch Monte Carlo case, except that instead of moving an electron, we're imposing this new lattice structure on a fixed set of displacements. So in the electron transfer case, the atoms aren't allowed to move, and you transfer a charge. Here we're forcing the same displacements without allowing them to change to accommodate a new polymorph. And what we know, and this is really what makes this idea so powerful in electron transfer, is that we know that the Bennett-Zwanzig relation relates the two free energy curves to each other. If you compute one, you get the other one for free. That is because the free energy of Diabat for state A minus the free energy of the Diabat for state B is just given by the value of the order parameter itself. And so these two things always have a gap, right here at this magical place that in electron transfer theory is a transition state, is a gateway state for the polymorph transformation process. And it's that place where the delta E goes to zero. So the analogy here is that electron transfer involves a sudden redistribution of charge at the same atom positions. In a lattice switch between two polymorphs, we have a sudden imposition of a new lattice with the exact same displacements. And so my student Kartik Kamat and I got excited about this, and we wrote a paper in 2017 that shows that indeed crystals, this analogy really holds. You can get diabats for the FCC state. This is a Gaussian core model. And diabats for the BCC state, they look like two parabolas. And what's really cool is that because of this Bennett-Zwanzig relation, you do the calculation in the FCC phase. This is no umbrella sampling, no advanced sampling whatsoever. We just do an unbiased simulation here in the FCC phase. and we get the red curve above it for free. When we do the simulation in the BCC phase, we're getting the blue curve above that for free. And so with two unbiased simulations, no umbrella sampling, no fancy machinery whatsoever, we generate the landscape over here, and we can get the free energy difference between the FCC and the BCC. It was pretty exciting, and we set out to see, these are Helmholtz free energies, I should point out, because the Bennett-Zwanzig relation was derived for an NVT ensemble with Helmholtz free energies. So we set out to try and do this for the NPT ensemble and try and get directly delta G, Gibbs free energy diabats, if you want. And we ran into some problems and had to do some statistical mechanics. Kartik is really good with that stuff. And he came up with this order parameter delta Q, which you can approximately think of as an enthalpy gap. And when you sample the enthalpy gap, you can show, no approximation here, that this gives you the Gibbs free energy diabat for species A minus Gibbs free energy diabat for polymorph B. And the idea seems to work pretty well. We get agreement with the lattice switch Monte Carlo results. That's the only test we ran it against, but it's two completely different independent ways of doing the simulation still. The disappointing aspect of this is that the curves are no longer parabolas. And I think that that's not really because we switched from Helmholtz to Gibbs free energies. I think it's because we got lucky with the parabolas in the first case. They have to obey this relation, this generalized Zwanzig-Bennett relation, but they don't have to actually be parabolas. It's very convenient when they are, and you get all these results basically for free compared to the other thing, but they don't always come out to be parabolas. Would love to explore this further and see if we can learn when to expect that parabolic approximation is going to work. So we're still pretty excited about this. You can see that our error bars do tend to be around half the size of the ones from LSMC with the same computational effort, and so there do seem to be some efficiency gains coming out of the Diabat approach. So we set out to try and do it for benzene and carbamazepine just to illustrate that we can do this for molecular crystals. We learned some things along the way. You run into a lot of problems if you don't preserve rigid rotations. So there are some cartoons here that show what can go wrong. But trust me, if you take a benzene molecule which can rotate sixfold, around its axis in phase one, and then you port those Cartesian displacements onto the same benzene molecule in phase three, you run into lots of distortions that you didn't expect. But you can devise a Gramschmidt local coordinate system for keeping track of these orientations. It's really general. Once we did this, we're able to plug in for different molecules and not do anything different. It's a black box code that allows us to keep track of these, and you can see now the molecules really retain their basic shape for rigid rotations. So we implemented this procedure. There's another caveat here is that we had to add springs. The certain directions in the benzene crystal are really easy to move, and when you take those displacements and you port them over to the other form, they crash into each other. So we had to suppress some of the motions by growing some weak springs onto each of the benzene molecules to hold it in place a little bit. But other than that, you can see that the whole approach does work. What's kind of interesting here, and a little bit disappointing, we'll come to that in a moment, is that our Diabat approach has been contaminated by the Frenkel-Ladd approach, right? So we've got a little piece of Frenkel-Ladd machinery in the Diabat calculation. And I'm going to show you what the effect of that is. The Diabat approach is still more efficient than the whole Frenkel-Ladd calculation, going all the way to where we dissolve the benzene molecule and just have the springs. But you see that it's only about a factor of 2 faster than the Frenkel-Ladd approach. And I'm the first one to say that a factor of 2 is nothing to really write home about. I am still hopeful, though, because when you break down where the effort came from in these approaches, you see that 7 nanoseconds of our sampling time went into the Diabat calculation, and 80 nanoseconds of our sampling time went into these 2 Frenkel-Ladd pieces. And so it would be wonderful if we could figure out how to get rid of these parts. And I think that there's hope for doing that. Bridgewater and Quigley published a paper suggesting that the expensive spring step may not be needed at all. I don't really know why it worked without springs for their model and didn't with ours. To be determined. Hopefully I'll be able to give you an update on this at some point. But you can see that if it's true that we can get rid of that, then we are more than an order of magnitude faster than the Frenkel-Ladd, and we're getting the same level of accuracy. all of the cost is really coming from these Frenkel-Ladd-like steps. So I set out at the beginning to say that we were going to be able to precisely compute these chemical potentials. Of course, I distinguish precise from accurately here because we'll never be more accurate than the force fields that we start with. So in order to separate those two issues, we looked at carbamazepine, a real pharmaceutical molecule with four different polymorphs. And those 4 different polymorphs give us the ability to look at 4 3 different thermodynamic cycles where we go all the way around a loop using pairwise free energy differences computed independently with our machinery, right? So that we can mix and match those things and see how well we're doing getting back to zero. And the idea here then is that when we do this, what we should get is 0 on this column every time. You see that we do accumulate a little bit of error as we go around the loop using 3 different chemical and different thermodynamic free energy calculations. But it's on the order of about 1/100th of a kcal per mole. So our precision is really, really great here, and I think that that's something that we found with the growth rate calculations and nucleation rate calculations that really helps not to get that small error in your driving force. All right, so this is just reiterating this point that we can use these cycles to confirm that we're getting precise results. And I am well aware at this stage in my career that if you introduce something innovative, chances are good that people will continue doing what they were doing before anyway. If you are going to continue using Frenkel-Ladd, one of the ways that people try to accelerate that, overcome the slow convergence in those methods, is to use different spring constants for atoms with different masses, or different spring constants for atoms with different mean square displacements. The original papers on doing that had some errors in the formulas, and so check out this paper if you're going to stick to Frenkel-Ladd. This is written with Don and Gramschmidt, just going back and resolving some of those things and testing them against some of the newer machinery. All right. So in conclusion, I thank you for listening through this tale about the slow and boring aspect of nucleation rate and growth calculations. But these chemical potentials, really everything else rests upon them, and we can't hope to do these kinds of calculations for nucleation or for growth and then plug them into crystallizers if we can't first compute the thermodynamic driving forces. So I wanted to thank Vikram Khanna and Kartik Kamat, who did most of the heavy lifting here on all the computational work. I want to thank Mark Josvik, who did the growth calculation that I featured there at the beginning. I want to thank collaborators Mike Doherty, Sally Price, Chris Burcham, and Susan Russell-Edens. And of course, I want to thank Eli Lilly for funding. I also want to thank the NSF and the Dreyfus Foundation for early funding that got us started in this area. And thank you, Talid, for the invitation to be part of this session.
Thanks so much, Baron. This was great. Very, very fascinating. Okay, we have one question. Make it a quick one, please, because we'll move on soon.
Great talk, Baron, as always. I have a crazy notion that maybe you can dispel or encourage. So I was wondering if, the case where you see the parabolas, that, you might expect to see them when the 2 polymorphs have a similar heat capacity and not when they don't.
I don't see the connection, but I know that you're better at thermodynamics than I am. So I'm gonna reserve judgment and just admit that I don't know.
Well, I'm just thinking that when you look at distributions of energies, the variance is related to the heat capacity.
Ah, okay, yes, now I see the connection. Okay.
Yeah. And then, okay. So now you're thinking about, pushing configurations away from the ideal lattice, and then you're subtracting 2 different kinds of energy, and you're looking for distributions of that.
Yeah. Oh, that's brilliant connection. Actually, thank you for pointing this out. Yes, I definitely did suspect that what was happening is basically that we're getting a breakdown of the central limit theorem, but I never thought about it in terms of the heat capacity and the fluctuation results. Great, thank you.
Thanks so much. Brilliant. All right.